All right, greetings again, everyone. Welcome to the second part of the video for section 8.6. And as promised in this section, we are going to be looking at graphing parametric equations using technology. And then we'll also look at some conversions between parametric equations and Cartesian equations. So we're going to start by learning to use our calculator to graph each of the following sets of parametric equations. So we have x equals 4 times cosine of t, y equals 7 times sine of t, and then x equals 5 times cosine of t, and y equals 2 times sine of t. So I'm going to, for this, switch over on my screen here to my calculator. And in order to do this, we first have to make sure that our calculator is in the correct mode, much in the way that we switch the mode in order to graph in polar coordinates. So the way that we do that is we simply hit the mode button. We go down to that same line where we change our calculator into polar mode. This time we go over to where it says parametric, or it might just say para on your calculator. We hit enter. And also for what we're about to graph, you want to make sure you're in radians mode. That would be important. And when we go to the y equals now, you'll notice what we're given are two lines to be able to put in our equations for each variable. So you'll see that each kind of group here has an x equals and a y equals. So what we'll do is go ahead and put in that first set of equations I had. So we had 4 times cosine, and we hit our variable key in this case. It'll give us a t this time. And then we'll do 7 times sine of t. And I'm going to make sure I'm on a standard zoom. So I'm going to press zoom and then 6. Make sure I'm on a standard one. And when you graph it, we get something that looks like this. And actually, I'm going to change my zoom to zoom and hit 5 squares so that it looks the correct shape. And there we go. All right, so you notice this gives us kind of this egg shape looking thing. That's interesting. And in fact, this might be a shape that you know and maybe you've seen, especially in a science class. This shape here is called an ellipse. Okay, and it's again used in lots of science applications, in particular in astronomy for the movement of planets around the sun. Those are models by ellipses. And I also want us to notice that our original set of equations for this was x equals 4 times cosine of t and y equals 7 times sine of t. And if we notice, if we compare that to what we see in the graph, we'll notice along the horizontal axis, or the x-axis here, it looks like from the center, we go 4 units in each direction. And there's a 4 here as the coefficient for that. On the vertical axis for the y values, notice that from the center here, it looks like we go up 7 in one direction and down 7 in the other, and there's a 7 there in front of that. Well, that's interesting. Okay. Well, let's go ahead and graph that second set of equations I gave us. So this time we'll go back to our y equals, and we'll change this. Instead of 4 cosine of t, we'll do 5 times cosine of t. Instead of 7 sine of t, we'll do 2 sine of t this time. And we'll hit zoom and 5, so it squares everything up. And in this case, looks like we get another ellipse shape. And again, if we look at our equations, we had x equals 5 times cosine of t, y equals 2 times sine of t. And again, comparing these numbers to what we see in the picture, for the 5 here, notice on the horizontal axis, we go 5 units in each direction. And then for the 2 here on the vertical axis, notice we go 2 units in each direction from the center. So it looks like for an ellipse in these parametric equations, when they're set up as x equals something times cosine and y equals something times sine, that the thing being multiplied by the cosine gives us the distance we go in each direction on the horizontal axis, and the thing being multiplied in the sine tells us in which direction we go on the vertical axis, or how much we go in each direction. Okay. All right, now before we go back to the slides, I also want to show how to do this on Desmos for those of us using that, because it's a little different. So I'm going to switch my screen here now to show Desmos. Okay. And if we're going to graph, say, that last ellipse that we saw, the one that was x equals 5 cosine t and y equals 2 times sine of t. In this case, the way we're going to do that is we're going to put a parenthesis and then put each of those equations in as if they're parts of a coordinate point. So for the x part, we had x equals 5 cosine t. So in our equation here, we'll do 5 cosine t as the x coordinate. And then for the y coordinate, we had y equals 2 sine t. So we'll do 2 times sine of t for that one. Okay. Now notice in this case, we only got like a little corner of the ellipse here. And that's because our values for t are just set between 0 and 1. And to do a full ellipse, we really need to go all the way around a circle. You think about ellipse as kind of a circular object, which means the values of t that we plug in need to go all the way around a circle, which means we'll start at 0 and go all the way around to 2 pi. And notice that now that gives us our full ellipse. Okay, so you can mess around with graphing other things on that. I should mention on the TIs, you can also change the values of t. So if we go to our window button here, and notice here there is areas, an area for you to put in the range of t values you want to be plugged in. So notice here it goes from 0 to 6.28, which is 0 to 2 pi. If I were to change that to say 0 to 1 and graph it, we'll notice we get the same little picture we had at first on Desmos. So you notice that changing the t values can change how your graph looks. All right, so going back to our slides. Just want to talk a little bit more about an ellipse. So again, we just talked about it's this shape here, kind of this egg-looking shape that represents, that can be used to model the motion of planets. And here in this picture, notice that they're calling, if you look at, here's the center, the distance that it goes out along the horizontal axis, notice it says negative a and positive a. So they're calling that distance a, which tells us that for our equation for x, we saw that the value a came from what was being multiplied by the cosine in that equation. So we could see that x is given by a times cosine of t. And similarly, you notice in the vertical direction, the y direction, that we go up b units and down to negative b. And again, the value being multiplied by the sine in the equation for y is what gave us that distance. So we see that we can write that as b times sine of t as kind of a general equation for an ellipse. Also up here in the corner, you'll see that this is the Cartesian coordinates version or equation for an ellipse. So it's given by x squared over that distance a squared, so that distance along the horizontal axis, plus y squared over b squared, so that, again, that distance on the vertical axis equals 1. And you can see that by identifying the values for a and b, you could convert between these two. Okay. All right. Let's look at converting from parametric to Cartesian. And so we're asked here in each of the following to eliminate the parameter t to find a Cartesian equation in the form y equals f of x or x equals f of y. And notice what this is telling us up here is if we're told that we can write this as y equals f of x or x equals f of y. Well, in the first one, we see that y is a function of x, but in the second one, x is a function of y. So when rewriting parametric equations in terms of x's and y's, it's okay to write either x as the input variable or y as the input variable. And often, kind of the situation in the problem will dictate that. So as an example, looking at the first one here. So we're given that x equals t minus 2 and y equals t cubed minus 1. We want to write this as a Cartesian equation. And the way we do that is basically by eliminating the variable t. And we do that by isolating t in one of the equations. And when we do this, we want to do the one that's going to be the easiest. And here we see that x equals t to the first minus 2, so it looks like it'd be fairly easy to isolate a t here. Whereas in the second one, we have t to the third minus 1, which means to isolate t, we'd have to do some like cubed root, which seems like maybe a little more work. So in that case, we'll do the second one. So we'll isolate t by adding 2 to both sides. Okay. And so when we do that, what we end up with is x, excuse me, not x equals. These cancel out. Whoops, not that. That's not what I meant to do. So the minus 2 and the plus 2 will cancel out. And so what we'll have is t equals x plus 2. And now that we have t in terms of one of the other variables, as you imagine, what we can do is take that and plug it in for t in the other equation. So what that would give us here now, instead of y equals t cubed minus 1, so we have y equals the value of t, which in this case is x plus 2 to the third. So notice that x plus 2 took the place of the t. And then minus 1. And that would be our answer there. Okay. So again, all we're trying to do is eliminate the variable t. All right, let's look at the second one. So here we have x equals 4t squared and y equals 8 plus 3t. Now there's a lot going on in both of these. However, in the x equals, it looks like that the t is squared, whereas in the other one, it's to the first power, which makes me think that it would be easier to isolate the t in that second equation, in the y equals. So we'll go ahead and do that. So right now we have y equals 8 plus 3t. We can subtract 8 from both sides. So when we do that, we end up with y minus 8 equals 3t. And then we divide by 3 on the right to isolate the t, divide by everything by 3 on the left. So these will cancel. And we're left with this t equals, looks like y minus 8 all over 3. Okay. So now we have t equals this, so we can take that and plug it in for t in the other equation. So what that'll give us then is x equals 4 times, and again, instead of just t, we'll plug in what we have for t, which is y minus 8 over 3. That whole thing squared. And in this case, we can actually leave it like that. Okay, we don't have to isolate the y, because as you notice over here, we were told that we could write x as a function of y. All right. Okay, last one. So here we have x equals e to the 7t, y equals e to the 4t. Hopefully you would agree with me that these two equations are essentially the same. So there's not a whole lot of, or I guess it doesn't matter which one we choose to isolate t in. So I'm going to do it with the first one. So we have this x, and that's going to be hard to read. Let's not do that, Cody. So we have x equals e to the 7t. And notice that here we have the t up there in the exponent. So we have e raised to a power. And how do we deal with that? Right, so what we'll do is take the ln on both sides, the natural log. If we do that, what that allows us to do then is on the right-hand side, bring the 7t down to the front because of our exponent rule of logs. So we'll have ln of x equals 7t times ln of e. You can check with your calculators, or you might remember that ln of e just equals 1. So this is like 1 times 7t here. So we have ln of x equals 7t. Can divide by 7 on both sides. 7's cancel out here, so we're left with t equals ln of x over 7. And notice that I can write this as, say, 1/7, or sorry, 1 times ln of x over 7. And hopefully you would agree with me that's the same as 1/7 ln of x. So I'm going to write it like that for a minute. And this makes sense more why I did that here shortly. But notice now we have t equals this 1/7 ln of x. So we can take that, plug it in for t in the other equation. So that'll now give us y equals e to the 4 times our value for t, which is 1/7 times ln of x. So we could do some simplifying there on the top. 4 times 1/7, make that a 4 over 1, multiply across. That'll give us e to the 4/7 ln x. And we could actually leave our answer there. That's a fine and dandy answer. However, there's also more we can do. So recall over here when we had ln of something raised to a power, we were able to take the power and move it out to the front. But recall that that rule also works in the opposite direction. So if you have something in the top front, you can move it up to the exponent. So I'm going to do that here. This 4/7 here is being multiplied by ln of x. So we can actually move that up to the exponent. Get y equals e to the ln of x to the 4/7. And then you may remember from PreCalc 1 that when you have e to the ln power, okay, those two functions are inverses, e and ln, which means they pretty much undo each other because they're inverses, which means they more or less cancel out. And so we're left with just y equals x to the 4/7 answer, or 4/7 power, excuse me. That would be kind of a more concise answer for that one. Okay. All right, that's it for now. Thank you for watching.